Hi, everybody. Welcome back. And today I will be talking about organic soil amendments of animal origin and their impacts on soil fertility. Sorry, just one second. Okay. So soil fertility can be defined as the capacity of soil to provide physical, chemical, and biological needs for the growth of plants, for productivity, reproduction, and quality, relevant to plant and soil type, land use, and climatic conditions. So last time we spent the majority of the time talking about the physical and biological needs to support crop fertility, soil fertility. And so today I'll be talking about the chemical side, basically nutrition. And I'm going to focus on nitrogen for a few different reasons. Nitrogen is essential for plant growth. It is an essential part of amino acids, proteins, nucleic acids, and the chlorophyll molecule. It's one of the most often limiting for crop growth, especially under organic production, for which biological amendments might be more heavily used or relied upon. But in any case, it's the pathway for nitrogen availability from biological products is different than synthetic products. And nitrogen is a nutrient which normally produces the greatest yield response in crop plants, promotes rapid vegetative growth, and gives plants a healthy green color. So it's so essential, and it's one of the harder nutrients to manage coming from biologicals. And so it sort of warrants some focus. Nitrogen, a little background here, starts out when it's coming from manure or chicken pellets or guano. It's starting out as organic nitrogen in its organic form. And these are complex molecules that require a breakdown process to form simpler organic forms before they are mineralized and become plant available. So on the left-hand side, we have the complex organic forms. And then on the right-hand side, these are the plant available forms. And so in order to have this breakdown, mineralization, and nitrification process, this is completely reliant on microbes. And because of that, the potential for mineralization is dependent on moisture and temperature. Nitrogen is also unique or requires special attention because of its relationship with the soil. It is dominant in the form of nitrate, and nitrate is negatively charged, and clay particles in the soil are negatively charged. And this form, nitrate, is the major form that's used by plants. And so because of these two negative charges, it's repelled by soil surfaces, and so it does not attach and bind and stay in place. Therefore, it moves easily when water is basically there. So it gets leached with irrigation, with rain, any of those activities. And so it can also be lost to the atmosphere during sort of wet, flooded conditions. It will denitrify and volatilize. So it's a highly dynamic nutrient, and that is also what makes it hard to manage and hard to ensure that we have in sufficient amount for our plants. And this is particularly relevant when we're talking about biological amendments from animal origin. So the carbon to nitrogen ratio, sorry, this should have been like a sequential thing, but let's go over this in the most basic form because this is going to be the background of much of the talk too. We talked about nitrogen last week because, carbon last week because carbon is the energy for microbes. And its fate when microbes are decomposing material, residue, compost amendments, it's either going to be assimilated into the microbial tissue, it's going to be released as microbial products like waste products, which we talked about last time in the food web, or it's going to be respired as CO2. Now, for the assimilation of by microbes of these residues, the nitrogen has to be assimilated in the amount determined by that C to N ratio of the microbial biomass. And that magic ratio is somewhere around 20:1. And what that means is that the amount of nitrogen required by microbes is 20 times less than the amount of carbon. So that 20:1 is that tipping point at which you can have no net release or immobilization of nitrogen. So in this little example, if there are both a low concentration of labile, easily available carbon compounds, and a higher amount of nitrogen with respect to what's required, that 20:1, there will be net nitrogen mineralization and release of nitrogen. So that would be, for example, if instead of having a 20:1 ratio of carbon to nitrogen, you had 20:2 or 20:3, which would be like, a 10:1, et cetera. You're lowering that carbon nitrogen ratio, then you will have a net release of nitrogen. Some of these macronutrients, phosphorus and sulfur, in these organic structures, these complex molecules, during this breakdown process, they're also converted into their inorganic forms. And so those will either be immobilized into the tissue of the microbes and used in their population buildup, or they'll be mineralized and released in the soil mineral pool. So first, let's talk about compost. Here's a compost spreader. Now, we did a series of incubations in which we looked at a wide range of compost and looked at what type of availability can we expect from compost. And so on the x-axis, we have weeks after incorporation, so time. And on the y-axis, we have available nitrogen. So this is plant available nitrogen. And to compare here, you can see we have the composted poultry manure and a composted yard trimmings. And so this composted poultry manure, you can see that initially, there's quite some amount of mineral nitrogen available for plants already. And within 6 to 9 or so weeks, that composted poultry manure will continue to mineralize and release nitrogen. It has this sort of slow, steady pace. And by 12 weeks, about 35% of the total nitrogen that was in that product has become available to plants. So if you do the math where you have a percentage of N in a product, you added in 5-10 tons per acre, and you calculate that you have applied a total of 100 pounds of nitrogen, well, what you would do here is understand that only 35% of all of that 100 pounds is going to become plant available this season. And this is assuming like a summer season, a warm season. So you would get 35 pounds instead of 100 pounds. If we look at composted yard trimmings, they tended to basically hover around 0. Sometimes a little bit of a net release and sometimes an immobilization. So it was hovering right around net 0. And this is important to recognize. The main differences are two: the total amount of nitrogen and that carbon to nitrogen ratio. So in this composted poultry manure, that tended to have about 2% nitrogen as opposed to a yard trimmings, which has about 1%. And then the carbon to nitrogen ratio in the poultry manure tended to be closer to 6 to 8, whereas yard trimmings composted was up around 15 or so. So big difference in an animal-based product as opposed to a plant-based product when looking at compost. So in conclusion for compost, over those 3 months, 3 to 35% became available. We're going to visit that in a minute. So here's that little summary. Slaughter products. These are generally all of animal origin: bone meal, blood meal, feather meal, fish meal. And these tend to have high nitrogen, often with low other nutrients. They tend to be 12-0-0, for example, low P, low K. The exception is bone meal, which can be a little bit lower in N and a little bit higher in phosphorus and calcium. They start out with low mineral N initially, but then release very rapidly. And some of these products are being made now so they can be soluble. When we just look at the slaughter products, we look at this yellow line. And so you can see that it started out as 0, but within a week, more than 40% of all of that nitrogen has become available. So it's very rapid. And by 6 weeks, essentially all that will become available this season has become available. And so it's a very short-term, quick-release product. And both within our studies and across the literature, it was pretty common to have a release rate of 60 to 70% become plant available N. That's what PAN means, plant available N. Now looking at granular fertilizers. So these are products that tend to be blends of other organic materials. They often can be treated to increase microbial activity, like whether they were heat treated or ground or pelleted. They may contain significant amounts of available N initially. One example of that would be guano. But chicken manure, for example, has a lot of ammonium in it initially. So things that like pelleted chicken manure, which is pretty common on the market. This would have about 10% of the total nitrogen is in a form of ammonium, and so it's ready to go and be utilized by plants immediately. That being said, because it's in that form of ammonium, if it's just surface supplied, it actually would most likely volatilize. So you would want to incorporate it into the plants. So when we look at the granular fertilizers and guano, we can see there are two curves here. So let's just look at granular fertilizers first. We see just over about 20% immediately available, and a pretty nice consistent curve that by 6 weeks, most of what's going to be released is going to be released, with a little bit more coming over time. And that comes in at about 50% of the total. And we look at guano. Guano had a really high amount initially, more than 50% was available right away. And we see this really steep curve. In the first 6 weeks, you've gotten everything you're going to get out of there. That's about 90% of the total. And so these types of granular blends have this big range, but you can see how those sort of fall out based on the product. Liquid, this is another one that's pretty common. These can be fish, plant, guano-based, and they're designed to be immediately available. Hydrolyzed means it's been heat treated with enzymes. Emulsion also means it's been heat treated, and they're all meant to facilitate quick availability, quick accessibility to the microbes, and for immediate use. So when we look at the liquid fertilizers, the liquid amendments, that's here in purple. And it really is so close to these blood and feather meals, but you'll see it right there. So it has a little bit immediately available, but within even those first 3 weeks, you're going to get the bulk of that nitrogen right away. There is evidence that the liquid fertilizers of animal origin tend to have a higher release rate in the short term than the plant available ones. So these tended to have 50 to 100%, 50 to 90% release. And those will be things like food waste, for example. And the animal origin products would be things like fish emulsion. So they do tend to have a little bit higher availability when they're from animal origin. So here's a summary table of what I've just covered. And so what you'll see and notice here, and we'll look at in a minute, is you can see this carbon to nitrogen ratio, it generally decreases as we go from compost to like a 442 granular fertilizer to those slaughter products to guano. And you'll see that the N availability goes from low to high. Here's that yard trimmings just hovering around 0 to the poultry manure compost at 30 to 35%, up to these slaughter products at 65, 70%, and to guano at 80 to 90%. And so what we learned and what is evident across much of the literature is there's a very tight correlation between carbon to nitrogen ratio and available N over time. And the turning point is right somewhere in here, between 15 and 20 to 1. And that's where we talked about earlier, being the carbon to nitrogen ratio of microbes, microbial bodies, microbial metabolism. And so this is a really good indicator of what you can expect. It's the decisive factor for nitrogen release from organic matters. This is a really simple way to take a piece of information that you can gather from a supplier and immediately get a decent sense of what to expect. So if we're only getting a portion of the nitrogen now, where is it all going? So it's all going towards building your soil organic matter. It's being built into microbial bodies. It's feeding that soil food web. And so I'd like to share with you this figure, which is going to model for us the continual application of the same amount of organic nitrogen in each year, which was 43 pounds per acre, from a manure-based compost. So we're going to follow the blue color, and the blue color is 43 pounds of nitrogen that was added in the form of compost. And you can see of these 43 pounds, they got about 12 pounds. So that was 33% of the 43 pounds became available in year 1. In year 2, a little bit more was released. We got 16% of the total. In year 3, another 9%. In year 4, another 4%, 2%, 1%, etc. So you can, and then this is, the green color is, okay, 43 pounds was added in year 2. Now the orange, 43 pounds was added in year 3. Year 4 comes, another 43 pounds. So you can see how an annual application can lead to a steady state. And this is achieved right here around 4 years, at which then the system will start to hum and you'll get a more predictable, stable amount of nitrogen coming from the buildup and breakdown mineralization activity of those microbes and the food that you're feeding them. So revisiting this definition and to revisit some of the things we talked about last week, it's not just about nitrogen, soil fertility, although that is a big component of it. And so I wanted to share with you a study, and this was a study, a 25-year fertilization experiment in southern China. So different conditions, but long-term studies are quite unique. And so what they found was that crop yield, that they were comparing treatments using synthetic fertilizers and manures, and they had about 8 treatments of different combinations. And what they found was that crop yields were higher in all treatments with manure compared to the check and synthetic fertilized treatments. They also found that the synthetic fertilizer affected yields by weakly increasing soil nutrients and decreasing soil organic carbon and pH. And that the manure affected yields strongly by increasing soil nutrients, soil organic carbon, and soil pH. So we'll look at that for a minute. This is the yield. And what I want to point out is it's 25 years of data. And all of these with an M mean they had manure added. So they had 3 treatments with an M, they had a check, and then they had 3 treatments of N, NP, and PK. And what you can see is this separation here and then here are the products that all contained manure. And so you can see how those with manure basically started to stabilize or increase yield, and those with the synthetic fertilizer were decreasing. So it took several years to split up, but they split up. And when they looked at that yield difference, most of that increase in crop yield can be explained by three things: soil nutrients, soil organic carbon storage, and the soil pH. Soil nutrients are the major yield limiting factor, and therefore to achieve an efficient and profitable crop, it relies on large inputs of synthetic fertilizers. However, we recognize that less than half of total nutrients provided by synthetic fertilizers is effectively utilized, and much of it is left over in the soil, and that it does have, especially nitrogen, negative ecological effects. So the soil nutrients are a big part. Soil organic carbon is a really important one because this is not only increased because of the actual carbon from the manure, but it also influences the way of the cycling in the soil and the sequestration and nutrient release. And lastly, pH. With continual additions of synthetic fertilizers, that tends to acidify the soil, driving it down. And that has received considerable attention because it has negative impacts on productivity and soil fertility. It can not only increase the potential for heavy metals to be released, but also it impedes the activity of the microbes, which we discussed in detail last time. And here's a visualization of the impact on carbon. So here's MMM. These three are all the manure treatments. And the white bars here are the amount of carbon that's coming from the manure as opposed to the amount of carbon coming from the crop. So you can see how much manure is physically adding in terms of carbon. So it's a tremendous contribution. And there's a strong correlation between soil organic carbon storage and the annual carbon input. And that's what you can see here. So the more annual carbon input, the higher annual carbon sequestration. So that's really important to be adding a lot of carbon if we want to be sequestering and holding carbon in our soil. And remember, that's the food source for the microbes and all of their activity. So last two slides here. Long-term effects of organic management on soil fertility. This is from a paper, and so it's on organic management, but that's not necessarily an important feature here, but rather that there's a lot of reasons for amendments of biological origin. So first of all, what are the effects? There are many effects, is the first takeaway. Second is that the repeated application of organic matter to cropland led to an improvement in the soil biological functions. We talked about that a lot last time. The microbial biomass carbon increased a lot. The long-lasting application of organic amendments increased the carbon by up to 90%. And the regular addition of organic residues, particularly composted ones, increased soil physical fertility, aggregate stability, and the bulk density. It improves the bulk density. So I hope this is bringing together part of last week's discussion. And the best agronomic performance of compost is often obtained with the highest rates and frequency of application. So we continually need to be feeding our soil, feeding our microbes. The crop yield increased by up to 250% by long-term applications of high rates of municipal solid waste compost. And that organic amendments play a positive role in climate change mitigation by soil carbon sequestration. And that repeat application of composted materials enhances soil organic carbon, storing it for mineralization in the future, etc. So it's hard to separate out the biological, chemical, and physical benefits of adding biological-based products to the soil. But they are all working towards this concept of soil health, soil fertility. This is a slide from last week on some of the topics outside of soil fertility that we talked about, disease suppression, etc. So that's my talk for today. Thank you. And please stay in touch. You can subscribe to my newsletter, visit all this information on my website, my YouTube channel, and on Instagram.